Alright, in this video we're going to go over some integral properties and theorems. Alright, now that we know how to do integrals, let's look at some unique properties, okay? First one, if you have the integral of f of x dx, alright, so you're going to take the any derivative of some function f of x and you were to integrate it from a to a. Alright, so from the same number to the same number, like say from 1 to 1 or from 2 to 2. So you're not going anywhere, basically. That will always come out to 0. Because think about it, after you do the antiderivative, you're going to do f of this minus f of this, and if it's the same exact thing, it's going to cancel out when you subtract it. Alright? Also, another one. If you have the integral and you're evaluating from a to b, f of x dx, that is equaled to negative the integral from b to a of f of x dx. Alright? So, you're going from the same interval, but now you're going backwards. Alright? So instead of going from, say, 1 to 3, now you're going from 3 to 1. So it's going to give you the same absolute value, but it's going to be negative. So if this gave you a negative number, this would give you a positive. If this gave you a positive number, this would give you a negative number. Alright, let's look at a quick example of that, shall we? Alright, let's look at x integrated from 1 to 3. We're going to prove that that equals negative 3 to 1 x dx. Alright, we're going to prove this. So, when you integrate this, you're going to get x squared over 2, 3 to 1. Alright, so when you put a 3 in there, you're going to get 8 over 2 minus, put a 1 in there, I'm sorry, you're not going to get 8 over 2, you're going to get 9 over 2. 9 over 2 minus 1/2, which equals 8 over 2, which equals 4. Alright? Now, when we integrate that, again, you're going to get, so this here equals 4. I'm going to write it down here. Now, let's do the same thing, but go from, let's do it backwards. Put in a 1 squared over 2, that's 1/2. Put in a 3, that's 9 halves. 3 squared is 9 divided by 2, so that's negative 8 over 2, which is negative 4. Negative 4. Alright, so now you see that when you integrate it the other way, so here when we did this we got 4, here when we did this we got negative 4. So as you can see, when you reverse your to and from, you reverse the sign on your answer as well. Alright, you reverse your sign on your answer as well. Alright, let's look at another property now. So here we have the integral from a to b of some function f of x dx. Alright, this is the same thing. Alright, if we picked a number between a and b, let's call it c, and we integrated it, and then we added that starting at c and then finishing up at b, so now we've gone the whole distance from a to b. Alright, if we broke this up into two different subintervals, a to c and then from c to b, the sum of these two is going to equal the sum from a to b. Alright, so basically if we had a function here, say we had y equals x squared, it's only the positive side, and say we were integrating from 1 to 3, alright, as you can see, well, that'd be up here at 9. Alright, as you can see, we would integrate this entire area. This would be a and this would be b. Well, if we picked a number in here, c, alright, this first integral, alright, is going to cover this part, whereas this second integral, let me change colors, is going to equal this part. So as you can see, if you add both of these areas together, you're going to equal the whole area. All right? So if you pick some number, c, in between your interval from a to b, all right, and then integrate from a to c and add that to the interval c to b, it's going to be the same thing as if you just integrated the whole thing at one time. All right? Pretty simple. All right. So, let's look at an example. Let's look at a different example. Say if the integral from 0 to 2 f of x dx equals 6, and the integral from 5 to 2 of f of x dx equals 12. Find, okay, from 0 to 5, f of x dx. All right? So, we're going from 0 to 5 and then going from 5 to 2. We want to figure out the value if we went from 0 to 5. All right? So as you can see here, this equals 6 and this equals 12. But if you notice, these are reversed. Okay? Since they're reversed, remember, it gives us the negative answer. All right? It gives us the negative answer. So if we went from 2 to 5 and got 12, all right, what would we get going from 0 to 5? Well, if we were to flip this over and make it from 2 to 5 of f of x dx, what would it equal? Go back to what we just went over. What would that equal? Well, remember, when you flip these, it equals the negative value. So this would equal, here, would equal negative 12. All right? So what would the whole distance equal? Well, all we have to do is add this to this, and 6 plus negative 12 is negative 6. All right? So we don't know what the function is, but we can say that the integral from 0 to 5 of f of x dx is negative 6 based on our properties of integrals. All right? We know 0 to 2 is 6. We know 5 to negative 2 is positive 12. So when we flip these, we know the sign on this number is going to flip. So we flip them 2 to 5. We know that's negative 12. Add the 2 together, negative 6. All right? Not too bad, right? I'm just getting started. All right, let's look at a different one. I want you to try this one. So I'm going to leave you some time to do this one. This is just like what we just did. So say from 1 to 6 of f of x dx, it equals 15. And from 3 to 1 f of x dx, it equals 4. What is 3 to 6 of f of x dx? Good. Solve it. Okay, so there should have been enough time to solve it. So if we know from 1 to 6 it equals 15, all right, and from 3 to 1 it equals 4. Now, remember, from 3 to 6, all we have to do is take this value and subtract it from this value, okay? But this is backwards, so we need to flip this, all right? So when we flip this, make it from 1 to 3, it's going to turn into negative 4, all right? And we know that this here is going to equal the 1 to 6. Okay, the 1 to 6 is going to equal the 1 to 3 plus the 3 to 1. Okay? Okay, so it's going to equal the integral from 1 to 3 plus the integral from 3 to 6. Okay? That's what this one equals. Well, if this is negative 4, alright, so we have negative 4 plus, we don't know what this is, but we know it equals 15. All right, 15 equals negative 4 plus x. Simple algebra. Add the 4 to both sides. X equals 19. Okay? So, just based on our theories, we know that this will have to equal 19. All right? Let's look at another example. Actually, no, we're not looking at another example. We're moving on to the first fundamental theorem of calculus. So first fundamental theorem of calculus. All right, first fundamental theorem of calculus. It says if f of x is continuous on the interval from a to b, and f of x is the antiderivative of f of x, then, all right, it's kind of wordy, then the integral from a to b of f of x dx equals f of b minus f of a. All right, that's kind of what we've already been doing. We know that. You integrate this from here, you subtract this. That's kind of the given. But we can take this a step further. All right? We know that negative a to b of f of x dx equals negative f of b plus f of a. All right, that negative changes the signs on both of these. Okay, remember this was f of b minus f of a. Well, now that it's negative f of b plus. Basically, all we did was distribute the negative through. Okay, well, the second one here we can do is negative the integral a to b of f of x dx. That also equals f of a minus f of b. Okay, so here, the negative, instead of subtracting b from a, instead of subtracting a from b, I said that backwards, we're subtracting b from a. So we're basically doing the reverse of it, okay? And also, last thing, from a to b of f of x, all right, negative times the integral a to b f of x dx, that also equals the integral from b to a of f of x dx, all right? So, a couple theorems. Now we're getting into the second fundamental theorem of calculus. Okay? Calculus has two fundamental theorems. All right, so this is our second fundamental theorem of calculus. All right? So, if f of x is continuous on any interval containing a, then, all right, the derivative of the integral from a to x of f of t dt equals whatever this function is evaluated at x. Okay? It equals whatever this function is evaluated at x. Alright, so if you take the derivative, so if you took the antiderivative, evaluated it, and then took the derivative of that, alright, you might as well just take f of x, evaluated at x, and boom, you're done. Take f of t, evaluated at whatever this number is, and you're done. Alright? Because remember, the derivative and the integral are opposites and cancel each other out, so to speak. Okay? Let's look at an example because I know you're probably asking questions. Well, you probably have that puzzled look on your face as to how can that be. All right, let's look at one. All right, for this one, I'm not going to put an interval. I'm just going to do the derivative of the integral of x dx. All right. So when you integrate this, you're going to get x squared over 2 plus c. All right. Now, when you take the derivative of this, okay, remember, you're going to drop this down. It's going to be 2. So the derivative of this is going to be 2x over 2. The c's gone. The 2's cancel. Boom, back to x. All right? So if there had been a number up here, regardless of what this number was, if there had been a number up here, all we could have done was said, hey, it equals that number. So if this was a, from a to, no, I don't want to use b, I don't want to use x because it's right there. Say this was a 3. All we've had to done is say this equals 3. Okay? Because as you can see, everything else canceled. We took the antiderivative, took the derivative of that. Everything else canceled out. We're back to x. All right? Now, let's use a problem that has some numbers in it. Okay? Let's do... What do I want to do? Well, let's look at it backwards. The integral of the derivative of x, okay, dx. What's that going to equal? Well, the derivative of x is 1 dx. So now the antiderivative of this is x, of course, plus c. Because you can't forget your plus c. All right? But what about something like this? Take the derivative of the integral from 2x to 2 of t dt. What's that going to equal? Well, you might jump quick and say that it's 2x. Okay? But in this case, all right, in this case, we're going to take the 2 and multiply it by the 2x, and that's going to give us 4x, all right? Let's do this the long way now. But the answer is going to come out to 4x. All right, let's do this the long way. Okay, so we have the derivative of the integral from 2x, or from 2 to 2x of t dt. All right, you take the integral. So you have d over dx, and that comes out to t squared over 2, and we're going to evaluate that from 2 to 2x. All right, so you put in the 2x, and you're going to get 2x squared over 2 minus 2 squared over 2. All right, so when you square this, you get 4x squared over 2 minus 2 squared is 4 divided by 2, which is 2. Well, this cancels out to a 2, so 2x squared okay, so we have 2x squared minus 2, and now we're going to take the derivative of that. So the derivative of 2x squared minus 2, and of course this is gone. You take this over here, 2 times that, so this is 4x. So when you have a number down here, and not just a, when you have a number down here, this is going to give you f of the 2x, okay, times f of the bottom, okay? So it's just 2x times 2, which is 4x. So just evaluate at this, times, evaluate at that, and boom, you're done, okay? All right, what happens if you have a trigonometric function in there, though? Okay, say we had a trig function in here. So we want to do the derivative of, okay, x squared to 5 of cosine t, oops, it's supposed to be cosine, not cotangent, cosine t dt. All right, now, this one we're going to have to take the derivative of this and evaluate it at both of these. Where the derivative of cosine is sine, so we have the sine of t And we're going to evaluate that from 5 to x squared. And then after that, we're going to take the derivative of it. Well, when you evaluate this, you're going to get sine of x to the fifth. Where did I get to the fifth from? It's x squared minus the sine of 5. That should be a 2. All right. Now, we're going to take the derivative of that. All right, when we take, this is going to be a constant, so that's gone. So we're just going to take the derivative of this guy. Remember, this has to be chain rule. So you take the derivative of the outside, which is cosine times x squared, times the derivative of the inside, which is 2x. So this here is our final answer. So as you can see, the shortcut to this, when you have a trig function in here, all right, and you have a variable up here, it's just the cosine of that variable times the derivative of that. All right, so the cosine of x squared times 2x, which is the derivative of x squared. All right. Let's look at one more example involving sine. All right, I'm going to do this the shortcut way, and we're actually going to do 2 more examples. We're going to do this the shortcut way. D over dx of the integral from 7 to x cubed of the sine of t dt. All right. So, shortcut way, it's going to be the sine of x cubed times the derivative of x cubed, which is 3x squared. All right? That is your answer. That is the derivative of the integral. All right? And now, this also transfers over, but one more example. I promise this is the last one. I know I've said that for the last few minutes. One more example. What happens if we did the derivative of the integral from 4 to 7x of e to the t squared dt? Again, this works just like it did. You sub this in. So we're going to have e to the 7x squared, which is 49x squared, times the derivative of 7x, which is 7. So you can combine all that down to 7e raised to 49x squared. Okay? So, when you get to class, we're going to do some more problems on this. I had 2 more examples, but I'm going to spare you because it's just more of this. Alright? So, this has been some integral properties and your first and second fundamental theorems of calculus. So, make sure you understand what we're doing here, and see you tomorrow.